Hey everybody, can you hear me nice and loud? I know the sound in this auditorium can be a bit hard, so I might not hear you, but that's okay. All right, so my name is Etienne Caron. I'm an Android GDE. I'm soon to be a mobile dev lead for Shopify starting next Monday. I'm somebody that's very passionate about VR, which is the main reason I'm here today and talking in front of you. So thank you for having me. Right, so when I started making a cardboard app, I had a lot to learn. I'd only played around with 3D graphics. Things kept breaking when I changed little details, and it was a fairly painful experience. And since I'm not a very sensible person, I kept going, and I wanted to share with you some of the things I learned about so that you may benefit from my mistakes. Right, so here's a straight definition of VR. I actually think you shouldn't pay too much attention to the distinction between AR and VR. It's way too limiting. Now that being said, we still need to think about the core concepts that are at play here. You could look at VR as a simple feedback loop. You have various types of input that are fed into a simulation, which then outputs visual, audio, and haptic back to the user. If you play your cards right, that will give you absolute immersion, right? That's your goal. That's nice, but you might be thinking, I am an app developer, not a game developer. So how will I actually build this feedback loop? And some people have asked me straight up, why should app developers even be interested in VR? I'm not planning on becoming a game dev. Actually, any game developers in the audience today? Yeah? Anybody planning on becoming a game dev in the audience? Right, so you can relate to this, right? And it's actually a fair point. I can only give you my own personal take on all of this. If your goal as an app dev is to build new and compelling software, I actually strongly believe that VR and AR will offer great opportunities to do just that. Like obviously trailblazing is hard, but it can also be very rewarding. So let's talk about ecosystems a bit. You're sold on the idea. We want to explore new horizons. What's the payoff? Where are we going? So the key success to an app is to generally build a massive user base, right? That's one very obvious way to get somewhere. Let's see what the VR ecosystems look like. So right now, shipping in 2016, some of this stuff is already out. We have, as production head-mounted displays, the Cardboard and the Gear VR, which are successful headsets. We're going to have the HTC Vive and the Oculus Rift coming out now. Actually, this week or next week, we should see start stuff shipping. I think Oculus is already out. And the PlayStation VR is coming later this year. So, of course, there's associated ecosystems with each of these headsets. Cardboard has the Play Store. If you look at the top apps and their download numbers, you'll see it seems moderately successful. You're going to have the Gear VR with the Oculus Store, reportedly a great success. I actually haven't seen any numbers, but anecdotally, people I talk to who buy this headset tend to spend a fair amount of money within the first few weeks trying all sorts of things. And, the feedback is really good. Vive, so that's on Steam. Headsets are shipping in April, so we don't really know how successful it is or will be yet. But if you look at launch titles and them being the first to market for room scale VR, personally I believe it will be a great success. Oculus Rift, Oculus Store, the hardware will be probably just as good, if not better, who knows. Room scale is coming later this year, which is the big differentiator for the next few months. But the real question is, will the Oculus Store become a really viable new distribution channel? That's likely, but we're already seeing some Oculus-ready games on Steam. So it's kind of to be determined if Steam might not end up being one of the main sales channels for the Oculus Rift. All right. So where does this leave us, the app developers, right? So we really only have 2 or 3 distribution channels that kind of make sense right now. And we can see the successful ones, Oculus Store and Steam, are mostly focused on games. And the reason for this is fairly obvious. So money, right? That's what you want first and foremost for success, and a massive user base and all these nice things. So one thing we're now getting to with this generation of VR is an incredible level of immersion. Anybody that's tried the Vive will probably attest to that. And that will, without a doubt, revolutionize the business of selling content to consumers in a big way, right? But as app developers, we're not really in the business of creating content. We're in the business of creating software, tools. You could even argue in a way that games are actually content delivery tools. So again, if you're not a game developer, why should you even pay attention to VR? So at this point, we have to check if this video is gonna work. Just let me know if it's kind of glitchy. So to answer the question, I want to show you a bit about room scale VR. Who's seen the demos for room scale VR so far? Have anybody? Okay, so this is new information for you. Room scale VR is incredibly immersive because you can manipulate and interact with your simulated environment in a way that feels extremely natural. So I don't know if we can have audio on this, but you can basically see people manipulate these little toy cars that you have to build within the game. Could we, yeah, is it an easy, okay, is it this right here?
Plug that right in.
All right, so we'll give you guys audio. Good. Forgot to ask. So, yeah, all right. Well, basically the comments there are the person is thinking through the build that they're making for the game. So what's interesting here though is if you look at it, the matching of the hands with what they're doing is really, really close. They're building a thing in VR in a very natural way. Right, so imagine how this 3D game would work if you actually played it with a mouse and keyboard with a multi-touch interface. It'd be very different. It wouldn't be easy. I don't really think it would be a game anymore. We're seeing here a whole new interaction paradigm at play. One that can also be used for more business-oriented applications. All right, so VR is a whole new tool and you can manipulate objects this way. That's what we've said. In light of this, let's think of a few kind of applications we could build. So real estate, you could visit virtual houses. You could use it to, for architecture, interior design, computer-aided design, even sculpted and landscaping. All these things are possible applications. In Montreal, we have like people that do floor booth construction and show that off to their customers using VR. So let's say now we have a solid idea for a VR app. Awesome. What do we build it on, right? So right now, there's a lot of cardboard headsets out there, but it's fair to say that it's still a novelty, even if it is a popular one. The Gear VR headsets and the Oculus Store have seen good traction, as mentioned, so that platform is obviously attractive, but it's still more targeted toward games again. Right, so there is a dark horse in this race I'd like to mention now, and that's the Project Tango. Tango provides area learning, motion tracking, motion tracking and depth perception. So this summer, we're going to see the first Tango consumer device, a phone made in collaboration with Lenovo. It's way too early to tell if it will be a hit with consumers, but if you take Tango's sensor package, put it in a sub $500 phone, combine that with the current day cardboard SDK, and now you have an affordable augmented reality experimentation platform right out of the gate. So perhaps even an actual consumer base, like this phone might be a hit. So it's interesting to note that there's been strong rumors that Google has a couple of new headsets in the pipeline, and some people have been thinking that we might see a cardboard Project Tango powered head-mounted display coming out this summer. All right, so while we're visiting rainbows in unicorn land, let's take note of a few other interesting news items. There's Magic Leap, who's just got a massive VC cache injection that will apparently serve to build a new type of light projection device at scale. There's Project Soli, that's the portable radar as an input device. If you've seen the demos last year, fairly impressive stuff. That was seen at Google I/O. And there's Project Jacquard, which is Google's effort to turn prêt-à-porter clothing into an actual input device. So all these efforts are being designed from the ground up to deliver at scale. So we might actually be closer to Gibson's virtual light than we think. All right, so can't wait. If you want to explore AR right now, you want one of these two dev kits. The Meta 2 in the sub $1,000 range. That one has full Unity support, so that's interesting. And HoloLens has been extremely covered in the media. It looks awesome, but the field of vision is limited. And the dev kit has a $3,000 price tag on it, if I remember correctly. All right, so back to the real world now. We're going to start talking about development. We want to develop apps, not only games, that will be popular and successful. And all of this preferably in 2016. So what kind of tools can we use right now? Well, there's Unity. Who was here for Dario's talk yesterday? A few people. So we're not going to talk a ton about Unity today, but we're going to cover what it's good for, so you might want to explore it on your own. So it's actually very 3D friendly, it's got a massive community, it's easy for beginners, for C# and JavaScript is the main language used there. It's got wide support. You have a Cardboard plugin, a Tango plugin, Gear VR support, HTC Vive support, all these nice things. It's cross-platform, so you can work on Android, iOS, PC, what have you. The only slight problem here is that you have limited Android platform support. So if you want to develop for Android and want to use all the nice tools that we have at our disposal when making mobile apps, that's a bit harder. You're going to have to develop your own bridge to actually map out different functionalities in Unity and call them from the game engine itself. The IDE support on Mac, last time I checked, was kind of so-so. It's reportedly great on PC. If you're a Visual Studio user, you're probably going to be very well at home with that. So that's a very nice platform to work on. And if any of you actually do workshops or teach people, I would definitely recommend going with that first. That's the best way to onboard newbies into this stuff. It's pretty cool. Then you have Android Studio, a very rich ecosystem geared towards app development, full access to the platform's feature set, unlike Unity. You have massive amounts of open source libraries out there, the networking, the communication, the data handling, all these nice things. On the other side, you have fairly poor 3D management and manipulation, and the rendering tool set is a bit harder. It's harder to import 3D assets, although some external libraries do exist there. And OpenGL is admittedly a world of hurt. So obviously, given all of this, I decided to go with Android Studio for this talk. Right, so let's jump right in. I know it's late, so I tried not to be too spammy with code samples in this presentation. We're going to go over OpenGL theory, but in a very high-level way. So we're just going to talk about the basics and to sort of give you the language and the understanding that you are going to need to go through either the Cardboard sample apps, which we will not look at in detail today, but my goal is more to give you the tools so that when you do look at this stuff, you'll be ready and understand what you're looking at. All right, let's jump right in. So the minimum effective dose is to get a little bit of math and geometry concepts in there. So my thinking there is that Android developers on average don't play that much with OpenGL, so that's the worth. Euclidean space, that's just a fancy way of saying 3D space. When you're in 3D space and you want to locate yourself, you need 3 coordinates, x, y, and z. Then you have your vertex. In geometry, a vertex is a special kind of point that describes a corner or intersections. In computer graphics, it's actually a small data structure that describes certain attributes, like the position of a point either in 2D or 3D. And display objects are composed of arrays of flat surfaces, typically triangles, and vertices describe the location and other attributes of the corners of these surfaces. So vertices, plural of vertex. Primitives, right. So OpenGL assembles vertices into primitives. You can see that there's actually a lot of different primitives that OpenGL understands. And the reason there is mostly one for performance. Today we'll only be focusing on triangles because that's what you need to get started. For the curious, you can see what kind of optimization bonuses you'd get with other structures if you just look at a triangle strip. We're going to see that passing data around in OpenGL is one of the big performance hits. So if you can save some of the data, some of those structures are actually a better bet. But we're not going to go into that too much today, or at all, really. Right, models. So we're just going to add some terminology in here. Objects that populate our virtual world are just a collection of these triangles, and we call those models. An important point for understanding what comes next is that these models' coordinates, when you create them in memory, you usually define them around the 0, 0, 0 origin point. All right, so transforms. Why do we actually define the models around the origin point? This is done so that you can manipulate your model and move it anywhere you want. And you do this via 3 basic operations: translations, rotations, and scaling operations. The order in which you apply these operations is important, as you can actually see in this little diagram, right? So depending on the order, your object's going to end up in different places in the scene. This brings us to linear algebra. We kind of need to think back on that. So I'm guessing, well, the audience doesn't look that old, so college and university is not that far away, but if you're like me, you've been doing computer science for a few years, you haven't used that stuff all that much, right? So the important part to know here is that OpenGL and Android have libraries and function calls that takes care of all the heavy lifting for us, right? So you can forget about it a little bit and still operate. But if you do intend to explore 3D in a serious manner and it's all a fuzzy memory, your linear algebra, I recommend you speed play through a few courses online, right? Khan Academy has a nice one I saw, Udacity, Coursera, etc. Okay, so getting back to brass tacks. Projections and camera. Right, some more important concepts here. When you're going to be configuring an OpenGL pipeline, or you're going to look at code that configures an OpenGL pipeline, you want to set up rules of projection. You're going to see those being set up in the code. If you look at the first figure, the idea here is that you tell OpenGL how to project things. So you do that by telling it the bounds of the view, which are basically the bounds of your screen. You give it a top, right, bottom, and left. And you also configure it with a depth. So you have to define what is near and what is far. And by doing this, the values of your models, right, the values of these coordinates in your model are going to make sense to OpenGL, and it's going to know when it sees an object in the far distance how much perspective applies and how to project it onto your screen, which is a 2D surface. It's like the slice that you see in the diagram on the left. If you now look on the second diagram on the right, this one's to illustrate that you don't only need to place your models in the world to actually build a scene, but you also need to think about camera placement. We'll get back to this, but just understand that placing a camera in the world basically involves just another layer of translations and rotations that are applied to all the objects in the scene. In OpenGL, you don't move the camera moves the world. All right, so another very important thing in 3D, and that's true for Unity or OpenGL or what have you, is lighting. So lighting is one of the key things that makes a scene look realistic or not. So today we're actually going to learn how to implement Lambertian reflectance. So that's named after Johann Henrik Lambert, who introduced that concept in his 1760 book, Photometria. So yeah, don't worry, this is actually very, very simple stuff. We're only trying to anchor a couple of key concepts here. And those two for simple lighting are really only ambient and diffuse lighting. Ambient light is the light that reaches the surface of your object after bouncing around in a scene, and it basically can be estimated as a low-level light that permeates everything. It's like the base light that you have in your scene. Diffuse light, on the other hand, is the light that reaches your eye directly after bouncing off the surface of the object. So the sun shines down on the object, there's an angle there between that and your eye, and that's going to sort of determine how much light reaches your eye, right? And this is where the whole Lambert cosine law comes in. So to be able to calculate how much light hits your eye, you kind of need to be able to sort of figure out what's the difference in angle between those two things. And this is just a bit of context for the following slide, which covers normals. So what's a normal? This is basically what allows you to calculate that angle I'm talking about, amongst a lot of other things, but we'll stay on that for now. So what is a normal? If you forgot your math or if you never found out about this stuff, it's a vector that points perpendicularly outward from your surface. It is a normalized vector. Normalized because since we're only interested in calculating difference of angles, right, we can normalize all of this vector to a length of 1, which makes the math involved simpler and more optimized. All right, so vertices and OpenGL attributes. So we're getting ahead of ourselves here a bit, but I just want to try and establish a link in your mind between the nice theoretical concept we've just seen and the architecture I'm about to describe. So the idea is try to think of a vertex as a bag of attributes. The attributes we'll be playing with today are position, the normal, which you've just covered, and the color of the actual object. Also get used to seeing the vector type that you can see on the right, vec3, vec4. Think of these as arrays of floats, very simply. The suffix just indicates the length of the array. Last wrinkle, we'll see that OpenGL is a programmable graphic pipeline. That's just that just means that you can eventually add your own attributes to a vertex. So you can decide that a vertex also has a temperature, a velocity, and a direction, and then you could refer to that stuff in the programmable parts of the pipeline. So you don't only have to do graphics work in the programmable pipeline, which is something we'll touch upon by the end of this presentation. All right, so what is the OpenGL pipeline? Here's the full-blown OpenGL 3.1 pipeline, as you can find if you Google for the Chronos group. So how this diagram does, well, this diagram actually does a very good job of detailing all the moving parts and available options of that pipeline, but at this stage it's obviously way too much information, right? We want a bigger picture approach. So this is the simplest way of thinking about the OpenGL pipeline. It's actually very close to, it's what you need to have as a mental model to get forward. So there's a wealth of material out there. This actually comes from a specific example I found on Apple's OpenGL ES programming guide, which is actually very, very good. I would almost recommend, if you want to do OpenGL on Android, start with that document. Some of the top level view insights I got from this that I want to share with you. So the concept is, consider OpenGL as you would a typical client-server architecture. Your application pushes state changes, vertices, all the associated attributes, as well as rendering commands to the client side here of the framework. The client side then translates all this data in a way that the graphic hardware on your device will understand, and pushes all this stuff down to the GPU. Then the GPU does parallel processing magic, and you have animations and nice things going on. If you think in those terms, the client-server metaphor here, you can start thinking of performance in a way that's like close to communicating with a back-end REST server. If you want to process a big amount of data in one go, sure, the server is 100 times faster than your little dinky mobile phone, right? But you have to get the data to and from the server, and the network is a huge hit. And it's very similar in OpenGL land. It's pretty much how that works too. So the reason performance is super important is that we're looking at VR. Just to give you a reference point, the Rift and the Vive are aiming to get 90 frames per second just to avoid motion sickness and keep up realism. Your phone's hardware can usually do no better than 60 frames per second. Going below that is literally going to give nausea to your users in a big way. So performance is important. Keep things simple at first when you experiment if you want to get something interesting out of it. Right, so let's see the simplified version of the OpenGL pipeline. This is a simplified version of the big graph I showed earlier. Big things to note is the color code. So blue is your I/O. So this is where you're shuffling bits around. This is where you're pushing data into the pipeline. So at the start of it, we need to feed the pipeline vertices and the associated attributes, the very top. And we'll need to define how these vertices will be later be assembled into primitives by the pipeline. And again, primitives here is just a fancy word to say triangles. Yellow are for the programmable stages where you'll be running shaders. So who here has played around with shaders actually knows what that is? Few of you, so I'm assuming the rest of you are kind of fuzzy on what it is. So a shader is only a small script. It's literally a program written in a C-like language called GLSL, but it's very, very close to C. And you take this string, this script, literally a string, and you pass it to the pipeline, which will compile it at runtime. We'll have examples in later slides. But these programs are the programmable part of the pipeline we're talking about. So once you've got, the first programmable stage you have is the vertex stage. So the vertex shader will be applying transforms to all of your primitives. So you're going to have your shapes and your models that are going to be fed into that part of the pipeline. And that part will do the projection. We'll sort of say, okay, a triangle is going to land on screen in this space. Green, right after we see primitive assembly, that's the part where once you've transformed your scene and you've placed your models everywhere, it will basically assemble the triangles that will end up showing on screen. Then we have another yellow stage, which is the fragment stage, which is literally where you take your triangle and paint it onto the screen. Then after that, we get all sorts of little operations, alpha, stencil, depth test, and all that stuff. And ultimately, that generates a bitmap that will be displayed, in our case, on a GL surface view. All right. So I know this is a lot to take in, especially if you're just starting out. So this is sort of give another image to try to anchor that idea a bit better. So all I want you to remember is how you are passing basically from a vertex coordinate in 3D space right down to a grid of pixels that will be rendered on screen. That's going to help if you have a core understanding of that. So the vertex shader's job, transform the vertices into a primitive, and then those primitives are taken by the fragment shader, whose job it is to compute the colors of the actual pixels of those triangles on screen. So I have a little animation now to keep you interested. So you might be aware that GPUs are designed for parallel processing. So it might not have occurred to you why that's actually a good thing for graphics rendering. So here's a fun way to look at it. This is from a demo that the Mythbusters did at an NVIDIA conference in 2008. Is the video playing properly? I can't see on my own screen. Yeah? Cool. All right. Awesome. So the insight here is as follows. Each time a vertex shader runs, right, it works on a single vertex and its attributes. When a fragment shader runs, as seen in the video basically, you can think of a fragment shader as that massive paintball gun array. So the fragment shader runs to calculate the color of one pixel on screen. So the parallel processing here is that your program, your shader, is actually being run thousands or however many times in parallel to calculate the color of each of those things on screen. And the reason you can do this parallel job is because each of those shaders doesn't need to know the result of the one next to it to do its job. Like the only thing that's necessary to keep an order in is that you need the vertex shaders to run first in parallel, and then to feed all the result of that job into the fragment shader that will take these and also run in parallel and provide that result of pixel coloring to a bitmap, which will then be shown on screen. All right. So let's start talking about the actual cardboard SDK. That's a lot of theory, so we're going to look a little bit at what does this look like in Android land. So this is the regular Android OpenGL class diagram. Anybody's messed with this a little bit here before? A little bit, a few people? All right. So you have a few core concepts. The GL surface view here is the actual view that you put in your view hierarchy, where the results of all the OpenGL's pipelines work will be displayed. Right? It's very similar to surface view, and you create this class by creating an instance of it and adding your renderer to it, which is the class we see next to it, the GL surface view renderer. So the renderer is where the actual work and the actual code, custom code that you want, will be written. It defines the methods required for drawing graphics in the surface view. So mostly what you'd be implementing in there is the on-draw frame. This is where you're going to actually configure the pipeline or feed it the data that changes for each frames of animation. The important part to understand that's kind of different from the rest of Android is that you have an extra thread involved in here. So you have your typical UI thread, and when you create a GL surface view, you get an extra thread, which is the GL render thread. The thing that's kind of nice is that, right, this kind of simplifies things for us, actually, the way it's set up. The on-draw frame method of our renderer will be called repeatedly at a very high rate, totally decoupled from the rest of the UI. If we have movement in our scene, we can simply look at wall time or time elapsed since the last time that method was called to sort of determine where we are in an animation, right? We just look at the clock and say, okay, like 15 milliseconds, which is kind of a lot, was expanded between the last call and this call, so I should put the object that's falling into this space. If we need to communicate with the render thread, the fact that it's separate from the rest of the stack, it means that you need to use a call called queueEvent, which is similar to what you'd think if you're familiar with the way the looper works, and that will be then executed on its own thing. All right, anyway. So the Cardboard SDK itself is just built on top of this. At time of writing, so yeah, there's a little glitch here. So at time of writing, the Cardboard Java SDK, which means today basically, it needs to be included as a jar still. And that jar now includes native.so files, which is a new thing. If you've looked at Cardboard before, a couple year ago or so, it didn't have these native SOs in there. They've improved the library a ton, so head tracking is a lot better through this stuff, but the side effect is if you try to create an Android library module with it, you're going to run into various build problems. So my understanding is that we can expect a .aar, a proper .aar package sometime soon, but until that happens, you're going to need to basically put all your rendering code in the client app, like the app module of your project. So the good stuff is, though, that Cardboard Activity gives you some extra functionality, mostly to do with the configuration and lifecycle of the SDK, and the listener on the Cardboard's trigger, right? So you're going to have an on-trigger call, very simply, when a user presses that trigger. Very similar to a plain Android OpenGL app, you see that there's a Cardboard view that extends GL surface view. Cardboard view is where most of the methods to configure the SDK are found, and we're going to look quickly at that in a minute. So the Cardboard SDK itself, the stereo renderer is where most of your actual work is going to happen, very much like an OpenGL call in the regular stuff. It's not so far removed. The one thing you do need to notice is the two new methods, on new frame with the head transform parameter and on draw eye. So if you've been to some of the other VR talks during Droidcon, you might have heard something about the interpupillary distance. So the idea is that we've talked about cameras, right? So to create stereoscopy, really all you have is you have two different calls, and each of these calls is going to have a different camera representing each of your eyes. So you basically do the exact same work for each of these calls, except you take the parameter of the camera and you apply it. So for you, it's basically transparent. Your code is going to be called twice, but you don't need to think about it so much. Right, so just a small diagram there to sort of get you to think about the eye as the camera placed in the scene, right? Okay, so what does this look like in practice? This is your typical Cardboard activity. Nothing really out of the ordinary except for a few calls. Note the configuration of Cardboard view where we do set VR model enabled and the set distortion correction enabled. So those are the two big features, some of the big features that Cardboard brings you. So just need to turn the VR mode on, and if you've implemented the renderer correctly, you're going to get stereoscopy for fairly cheap. Yeah, if you want distortion, if you want lens distortion to be also applied, it's just a different call. The other thing we need to look at is how we set up our stereoscopic renderer. So what does this actually look like? So the two key functions of our stereo renderer, the first one, the on new frame with the head transform. In our case, we do basically nothing. Like, I'm not expecting you necessarily to get a super good handle on what's going on right here. I'm actually expecting you, if interested, to go and get the Cardboard SDK samples and start playing around with them. In our case, the on new frame, we're doing nothing with it because this call has to do with your head's position. And typically, you don't need to know this unless you're doing some sort of game hit detection, right? So it's only practical if you want to know where the user is looking at, if they're aiming at something, and you want to be able to say, okay, the user is aiming at this thing, presses the trigger, and then I do an action on the thing that's at the end of that. In our case, it's only a displayer, a renderer, so we don't need to do anything here. All of the action is going to be happening on draw eye. So we clear the frame. So the first call you're going to have is just wipe the screen, basically. The second part is you apply those matrix transformations we talked about earlier to project things in the right way. I'm going very fast over this, but I just want to give you a general understanding of how the code is structured and the big ideas, because I know that you have to review this stuff if you're really going to start playing around with it, right? And then once we've placed the camera, we pass all the information to all this information to the geometry object, and then there's a draw method that's going to be called. Geometry in this case, if you go look at the sample code, I'll provide the GitHub URL at the end. That's where the model itself is being fed into OpenGL and things like that. But if you follow the sample code I've put out, you can start playing around with your environments with fairly simple calls like this one. All right, so on to some live coding. In this case, I'm not actually going to be live coding. What I mean here is to have, I'm talking about the instance response cycle. The basic idea is that if your code compiles and runs instantly, you get to see the results in real time. You might be thinking, yeah, I think they call that instant run, right? So originally when I started working on all of this, instant run wasn't out yet. So I came up with a few methods that allow you to get instant updates and experiment a lot with 3D scenes without necessarily having to rebuild an APK every time. If you're interested about this stuff, I'll be releasing my deck after. There's a guy called Brett Victor that has a really amazing talk called Inventing on Principle, which might seem a bit of an odd title for what we're talking about today. There's the link, you should definitely check it out. He's basically pushed forward the idea, even before we had things like Swift and live updates of code, just to basically say IDEs are broken and we need to fix this. I think that live coding is an interesting concept to explore a bit more. Anyway, right, so an example, what does that look like? What do I mean? So I have a very simple 2D, 3D landscape here, which is inside a skybox. So as the code for this is shader code, by the way. So as the fragment shader code is being commented in and out, you can see that the skybox is getting a skyline, the sun coming up. So you can see also that these things are being updated in real time and from a simple Sublime editor. So what's fun here is if you know about, if you know about nothing about OpenGL and shaders and all that, once you have a setup going, you can start experimenting with it and really gain an understanding of what's going on much quicker than, say, if you had to hit your nose on the wall every time you try a new operation. So how did I build this homebrew toolchain? Just a quick explanation of it. It uses Gulp. It's a JavaScript build tools for those of you that might not have played with it, and something called Browserify, which is a library that allows you to convert Node.js code into browser executable JavaScript. I know, the J word. Gulp's flexibility actually made it pretty trivial to build a config that watches any change you make to those JavaScript files, auto-builds the Node package, sends it over to the phone, either through an ADB flow or even through Firebase, and then you will get a live update in the apps that are running your viewer. The Firebase part here is kind of interesting because some of the applications of this are, if you build a client that you distribute to 100 phones, you could live update the 100 phones on the fly, which has kind of interesting implications if you want to have a shared experience with people. You could think about DJ applications. I know that's sort of part on my roadmap, but you're welcome to go and check out the code samples and try to come up with something. And please let me know if you do. I'd really like to see what people do with this stuff. Right, so the other option, of course, now being instant run. So this is somewhat new. It doesn't take away the interest of the small toolchain I just showed you, because basically instant run adds the idea that you can reconfigure your OpenGL pipeline very quickly without having to build an APK, and you can experiment with that. But my personal experience with the OpenGL pipeline is once you have one that works and you can start playing around more with your scene, you don't want to touch it too much unless you are really thinking about something specific. So I think for experimentation purposes, instant run becomes really interesting when you dig deeper into OpenGL after you've played around with it for a while. If you were at the keynote yesterday with Chet and Romain, you might also have heard Romain mention OpenGL 3.2, which will bring geometry and tessellation shader support. Now, those shaders, what they do, they're extra steps in the programmable pipeline that actually can generate geometry, which is going to be very exciting. So there's sample code out there for desktop OpenGL where people do crazy things with that, and that also, is very open to experimentation. All right, so we're almost good on time. We have 5. I think we're closing in. I just want to now, 5. Okay, that's good. So I just want to expose you to ideas that you can research and get you excited to play with this stuff. So. Quick explanation how we move from vertex to pixel. So I showed this earlier. Blender is a very interesting tool if you want to do 3D modeling. I'm not going to say too much about that. Procedural content generation is awesome for a lot of reasons on mobile. There's a lot of sample code out there that allows you to create entire environments on the fly, and which is very interesting if you are living in a processor limited and a data limited and a network limited world like we are with mobile. Of course, Minecraft is like the prime example of this. You have a semi-infinite universe you can explore just with content generation procedurally done. I'm going to skip over these things. This is more like, you can look at the slides later if you're interested, but this is like in detail how to generate the models with the JavaScript example code. The interesting part is that if you want to start experimenting, it's very easy to define objects and play around with a simple array like this. And for example, if you want to generate things like a Minecraft landscape, here we have a small for loop that generates a randomized map of cubes with different heights. So that's using something called Perlin noise, which is a simple noise generator that maps out in 2D. And the resulting, is the video playing right away? And the result of this is as follows. So I just have a live coding example here. We're commenting out the cubes that you can see and pasting in the for loop that was shown in previous slides. And you can see that, and I can't see if you're seeing this, but. So yeah, we're commenting out the thing, and once we comment back in the landscape, you should see it pop up in a second. So yeah, this is basically what you get. So that's not a whole lot, a line of code to start having fun in a virtual environment. Right, so if you don't like Minecraft and you want to start seeing smoother landscapes, it's actually not that much more complicated. All you need to do is to create a plane with triangles that have varying heights, and you can apply the same Perlin noise method that's shown to the cubes, and instead of having the rough environment, you're very quickly going to have nice smooth planes all over the place. So I'll let that run just to give you a bit of an idea how quick and easy it is to play around with this setup. So I'm showing off here the code that was in the last two slides, but that's not that interesting. Just commenting out the call, and we're going to generate the plane. So, even if you're new at this, since it's relatively short code-wise, you can look at it a bit and get a quick understanding, play with it. So that can be interesting. All right. So what else can be explored like in this pipeline? So vertex shaders. What can you do with vertex shaders? You can do very fancy things. So if you go to the link on this slide when you get a chance, you basically can simulate this explosion effect using less than 20 lines of shader code, the vertex shader code, and about 10 lines of fragment shader code, and pretty much build that on top of the small kit, the small Android project I'm providing. So that's actually very simple stuff, even though it looks pretty good. Right. Pipeline, what else? There's some nice tricks out there. So I've been talking a lot about app development. So the stuff I've been showing you seems to be more oriented toward games. Well, if you want vector graphics to create UIs, how could you do it with this sort of simple technique? So some ways of doing this is by feeding textures into your shaders that actually describe how far you are from a point, a given point. You can use this technique to simulate vector graphics in 3D environments. So anyway, I'll let you, as an exercise to reader, I'll let you explore this a bit more. Another interesting technique that exists is full screen fragment rendering. So you can actually sort of trick the pipeline into only using fragment shaders. So the basic trick is you show two triangles to the user right up to their face, and you bypass everything that has to do with 3D in this environment. I'm almost done here. So what you can do with this stuff is as follows. The code for this simulation you're seeing here is all uniquely running in a fragment shader. You're actually looking at two polygons being rendered by a fragment shader, which you see the code on the right pane. That's not necessarily what I'd recommend you look at if you want to start out playing around with fragment shaders. But one thing that is interesting is on this shader toy site that I really recommend you visit, there's something called the 2-tweet contest. So these are shaders that fit within 2 tweets worth of content. And every single one of these that you can normally see being animated was written with 2 tweets worth of actual code. So you can get up to a lot of shenanigans and interesting things. So I really recommend you check out ShaderToy. It's a public repository of these shaders, the fragment shaders, and you can have a ton of fun. I've done a few things with fractal exploration in VR just by taking sample code from that site and adapting the cameras a little bit, and you can get up to very interesting effects very quickly. Time's up. So last point. We haven't talked a ton about UX. It could be a talk on its own. It eventually will be, hopefully. What I do recommend you do, though, if you're interested in exploring the space, is to download the Cardboard Design Lab app. It will explain things much better than I could in a 2-minute slide. They have really the best of breed patterns to follow if you want to get a nice app going. And that's about it for me. Thank you for your time. I really appreciate it. The GitHub link is there if you want to take a gander and go check it out. If you have any questions,